Jim and Antonino, which are joining us now. So Jim has been honoring me with his participation for many, many, many years, and even coming to visit me at my place in Wamar with Caroline and also Thuk and Cy Hammond. And then Antonino is the first time, so welcome. And this is a combined presentation, but we also share interest on the open source side of things, both in open source software and hardware. And they have been supportive of a lot of initiatives that we had in different conferences in supercomputing. And look at that, how nice is this? So, yes, this is.
All right. See if this is working. Oh, okay. Okay. So I'll go ahead and start. I thought I would add a comment on something that people don't know about myself. There's been a lot of discussion here about water from time to time, and Tuesday we experienced water in person. When I was an undergraduate, I spent a couple of summers working as a student intern for what is called the U.S. Geological Survey. And my position was a hydrologic aide. Now, what I did was perform maintenance on stream gauging stations. If those of you who don't know, a stream gauging station is basically a structure on the bank of a river that allows the stage of the river at that point in time, at that place, to be accurately measured. I look back on that, and that was actually an example of a distributed sensor network. You could periodically sample the stage of a river and all of the points along the rivers of her, in this case, it was the state of Illinois. But this is actually used to calculate when a river would crest, what the floodplain might be. So this is actually very important to understand, the predictions this is how we arrive at predictions on when a river will crest. If you're concerned with flooding and things like that. But I thought it was just interesting that that's part of my history. Antonino?
Yes. So I will add maybe two things, right? One is I'm obviously Italian, but it's about 3 weeks that I'm also a US citizen, so I will let you I will let you decide if it's as good about the thing. And the other thing that people may not know is that I have a room full of Lego, and that is getting basically an uncontrollable situation. And considering that I'm also Formula One fan, and there's kind of only one team, obviously Ferrari, but people have seen my backgrounds everywhere, so that I think is well known. But what is not well known is that Formula One and Lego now have an agreement. So I think my situation with Legos to build and build is going just to get worse. So,
Okay, thank you.
Yep.
So we are here to talk about a project called the Democratization of Co-Design for Energy Efficient Heterogeneous Computing. This is one of the DOE Office of Science Microelectronics Science Research Center projects. It is an example, or is actually an explicit example, of DOE's support for the CHIPS and Science Act of 2022. It took a while for the funding to work through, and formally we'll have to see what happens with our new administration. This is a list of topics that Antonino and I will cover. In fact, I will let Antonino provide the details of each of these thrusts, the co-design of energy efficient silicon in a package processors, our open source co-design tools, and our prototyping and chiplet integration thrust. This is an overview of the DeCoDe team. It is led by P&L. We have partners including UC San Diego, Andrew Kong for Open Road, and Diana Rosing for her work on hyperdimensional compute accelerators. Andreas Olofsson from Zero ASIC for all of his work in the open chiplet ecosystem. Tactical Computing Labs for their work on compilers for heterogeneous computing, architectural simulation, hardware generators. University of Harvard, David Brooks and Guiyong Wei for their work on architectural simulation as well, and a lot of experience in hardware tapeouts from Columbia, Luca Carloni and his ESP project, where he's done a lot of work on prototyping platforms and also has a significant amount of tape-out experience. Our collaborators from Washington State University have done a lot of work with architectural modeling, or I should say thermal modeling of chiplets, and in fact, the development of very simplified reduced order models to allow for perhaps even real-time control of power management for thermals. From the University of Maryland, Minnesota, I should say, Kevin Chow, who's done a lot of work also with thermal simulations and chiplets, and has a lot of, again, experience with tape-outs. Finally, from the University of Rochester, a group that's been doing a lot of work on CMOS-compatible icing machine accelerator. And Antonino will spend a little more time talking about both hyperdimensional compute accelerators and icing machine accelerators that are important use cases for us. Let's see, so the objectives of DeCoDe are really, when we talk about democratization, it is about lowering costs. And we really think about how we could step back, and maybe this is part of the answer to the previous panel question on what's the future of computing. Because we really think that we can reconceptualize the science and technology foundation for hardware-software co-design. And I'll make the bold statement that we all talk about co-design, and a lot of people talk about it, but unless you're working with FPGAs and four-screen reconfigurable arrays, you're largely responding to hardware designs that are coming from the vendor community. What we're talking about now is reconceptualizing the software, the science and technology foundation for co-design. We're actually thinking about how could hardware architectures actually be modified, designed, generated, prototyped, and then tested and evaluated. So it's kind of a different perspective on what is feasible in terms of hardware R&D for advanced computing. It's not possible without some of the investments that are being made by things like the CHIPS Act, but I think with the significant investments that are being made, and I spoke about this last year at Multi-Core World, we actually can talk about lowering the barriers for doing true hardware-software co-design. I've spent a lot of time talking about hardware, but the reality is there's a lot of software as well. And really, I am talking about restoring balance between the amount of software R&D we can do and the amount of hardware R&D that can be done. Let's see. Our objectives also are to support some of the recommendations from the President's Council of Advisors on Science and Technology. They identified some specific goals for the DOE to take on, which included energy efficient computing with new computing paradigms, edge computing integrated with sensors, And we think about that a lot in terms of our approach, which is a heterogeneous analog digital processor, because a lot of sensors start off with raw signals that are analog. And so the amount of computing that you can do and processing you can do in the analog domain will also naturally lead to energy benefits. So our core DeCoDe strategy is democratizing access to cutting-edge prototyping through an integrated portfolio of open source co-design capabilities. And Jeff was mentioning earlier that when you talk about hardware design tools, there are three big commercial vendors that have a lock on the EDA electronic design automation market. We think there would be a place for EDA tools that are open source. They're not designed for product, they're designed for prototyping. And I think if we can keep that in mind, that there's a lot of research that could be performed at a prototype level, then there's an opening for lower cost. And I think we're all used to the software world where you don't burden software R&D with regression testing, regular nightly builds, all the things that would impose on a production implementation of software. Why do we force ourselves to use production EDA tools if we're trying to do research? We're trying to change the paradigm here. Okay, so I have a few icons here on the right-hand side. They refer actually to some of my past talks, the multi-core world. I will also add that hybrid heterogeneous computing is a natural for energy efficient computing, because we always think about energy efficient accelerators that need to be integrated with conventional general purpose processors. And that's important for DOE, that we don't want energy efficient computing for just a narrowly specialized algorithm. But there's another role for heterogeneous processing, and that's for the converged workloads that we've been talking about. Most people think in terms of modeling and simulation and AI. In our data model convergence initiative, we also looked at data analytics in combination with the first two. Let's see, I'll just maybe repeat that the integration of analog accelerators and really custom digital accelerators and commodity CPUs and GPUs is a real element of our co-design approach. And the innovations we're trying to pursue in this project deal with the software side of composable heterogeneous computing, as well as the chiplet integration side. And with that, maybe I'll turn the microphone over to Antonino.
Thank you, Jim. And I'll go a little bit more in detail in our three trusts, right? As Jim was highlighting, we kind of focus on the ecosystem that will enable us to kind of design/generate these complex heterogeneous systems. So in the first trust, really the focus is to co-design the system in a chip, but more to co-design and understand what are the chiplets that can be composing this system, with a couple of new things, like obviously this is a research project, and it's going to focus on analog or exploiting analog computing for the accelerators. We'll explain a little bit later why I say they don't necessarily need to be completely analog, but like analog is giving, potentially the analog computing approach is giving an advantage. But like we are generating a system in a package, right? And the system in a package needs to be composed by a set of conventional processors or components of the shelf, right? That you want to compose and specialize. Even more, like obviously we have capabilities to generate custom accelerators. We'll show you an example to that. And like some of these chiplets can be the domain-specific accelerators, so that with just a few components, you have a set of many, even millions of permutations for configuring your custom systems, right? And one of the idea here, big ideas inside DeCoDe for democratizing is also trying to set standards and sustain the open source and the open chiplet community, right? Try to identify what are the right ways to kind of generate this common interface, at least for prototyping use that we can leverage. And to this, like adding the analog accelerator. I will show now. First kind of analog accelerator that we are going to look at is hyperdimensional computing. So this doesn't need to be analog, but like hyperdimensional computing is basically a computing paradigm, right? That is motivated, is neuromorphic because it's motivated by the observation that the brain operates on a high-dimensional data representation. Like how you represent this information is in hyperdimensional, so very long vectors, hypervectors, and like you don't care too much about the precision, like the precision you can decide, because it's really the dimensionality of the vectors that reflects the complexity of the input data. And like the larger, the more dimensionality you have, right? Obviously, there's more noise that you can tolerate because all the operations are kind of very simple to be executed. Like what you need is actually just similarity metric to understand if like your classification matches. That's why it's very brain related because that's how we work in the brain. But it's also like very noise tolerant because like you can just compare a vector of bit-based vector, right? Just computing mean distance to kind of understand doing inference of understanding if one vector is in the same class, right? Basically, hyperdimensional computing has really 3 steps. One is obviously encoding the data, then training the model, and then doing the inference. Encoding is just addition, multiplication, and permutation operation. You take your data, you convert it to the hyperdimensional vector, right? You may want to quantize or simplify your data, but it's really just very simple operation. In training, what you do is basically just doing, it's super simple, right? You just do a bundling, which is basically exploiting an addition of the hypervectors to the same class. And then when you do inference, like you encode the query vector, then compute, as I was saying, with the similarity metric. If you have single bit values, it's just a mean distance, right? Typical computer science distance that we always use it to compute. If not, you just use the cosine similarity, which is simple to implement. And given this, so this can obviously all be implemented in digital, right? I think we are also pretty good in implementing this on FPGA. But like, if you move to in-memory arrays, like Jeff was showing, this type of operation becomes very simple to be executed in the analog domain with a memory array, right? So there's a big opportunity here to exploit in-memory computing to do hyperdimensional computing because like you have this large array of bits, right? And you can just compute very simple operation with it. And that's an example actually of, this is digital actually, but it's an example of the tape out from Diana Rosin group in UCSD that actually is using hyperdimensional computing. This is, I think, 40 nanometers TCMC, but like there's the paper if you want to check if I'm correct about that. Moving to the easy machine, right? This is actually an analog chip, as Jim was highlighting, that there's already a tape out coming out from Rochester. A lot of work done on BRIM, which is a B-stable resistively coupled easy machine. All the concept for an easy machine is that they are kind of based on natural annealing, right? You have a dynamical natural system that seeks basically the lowest energy states. Can be water, can be chemical reaction, right? One of our project is actually looking analog computing as chemical computing. Also, Jeff was highlighting that. And the principle is the same, right? It's an analog system. It can solve ordinary differential equations naturally because it's a physical system. That's how you represent the physical system, and it converges to the lowest energy. So in the case of the Ising machine, the electrical Ising machine, this is CMOS compatible, which means that is an analog electronic dynamical system, and this is governed by the energy function, which is an Hamiltonian of the Ising model. So like in quantum computing, basically for the quantum annealers, what you do is having this Hamiltonian that combines the spin states with some coupling parameters, which is the correlation strain between the pairs of spins, right? And the spin self-reaction strength to the external influences. And then, like in the actual implementation, BRIM uses nanoscale capacitors where the voltages are the spin values, and then like you have programmable resistors to represent the coupling. And like you change the resistor values to get the different coupling. And so BRIM already exists, but like this is limited by the very simplified Ising model right now. What we are going to do is complete the support for cubic interactions and real values, because like the spins here, you see they are just 1 or 0, right? So the binary. And then like the other important part, because this is going to be in a chiplet, is designing the interface to set up and sample the results together with potential class of algorithms that we can map on this. A little bit more conventional chiplet library. We have many existing intellectual IP property blocks, as I was saying, like these 5, right? A sort of machine learning accelerators, GPUs like Vortex from Georgia Tech, all the zero ASIC examples already implemented with, like you see here, actually the chiplets that were taped out. But what we are really missing to generate a chiplet ecosystem is the standards: electrical, mechanical, communication, thermal, and testing, and the interface generators, right? If you ever listened to a presentation from Andreas Olofsson, it will always make the case that like the only thing that we have is UCIe, which is an electrical standard, basically in the protocol, but like it's missing all the other standards. So like you don't have this pluggable ecosystem. And like with DeCoDe, we hope to, at least for prototyping use, to start to define these standards, right? And then in collaboration with Trust2, which is the hardware design part, right? The hardware design tools and the compiler tools and the software stack basically help in the definition of these generators that will enable you, right, to take your accelerator, for example, and plug in the interface and then having the chiplet ready. Moving to Trust2, that's in fact the way that we think to expand our open source, really co-design tools, because it goes from compilers and hardware generators. Like there's a big need in the open source hardware community, and like it keeps hearing from me open source, as Nicolas was saying, because we have been with Jim big promoters of the fact that open source puts us in the lead user condition, where like we develop our own tools that then like can help support very important specific work, right? And only with the community converging, we can really build something that is greater than just adding the components, right? The sum is much greater than its parts, as usual. So in DeCoDe, what we'll do, we'll work on the algorithm part, creating the libraries to exploit this analog accelerator that I presented, and require the compilers. At least starting to think about what are the elements needed for a compiler, starting from DSLs, leveraging our previous work on that. Jim will show, hopefully, the slides with all the tools that we already have developed. We need the architectural simulation, because like we need to compose our system and see, get early estimations, right, on how things are going to be implemented. Thermal analysis, as I was saying, talking about thermal standards. There's nothing for chiplet. We need a thermal simulation. there's the part for the chiplet packaging and the co-design, like some of the work coming from University of Washington, Washington State University. Sorry, hopefully there's not anybody from UW or from Boissous here, don't kill me. But some of the work from Washington State University from Parta, and the work from Kevin Chow from University of Minnesota is going to look like on what we need to do the packaging, to do the splitting together with our friends in Harvard. And then, like, as I was saying, the interface generator, right? It's in collaboration between the Trust 1 and Trust 2, because like we'll need to set the standards, but then have the implementation through the actual generators. And this is a big picture, really, it's the big picture of the compiler infrastructure. But basically, I just highlight a couple of things here. What we think to do is obviously to exploit all our expertise in MLIR. You see, in fact, a lot of DSLs, because MLIR is great to develop DSLs. We think that for HDC in particular, and for the easing system, like you can use Kubo formulation for example for easing. So it's relatively easy. Needs to be taught, obviously, but like it's the perfect framework, I would say, to kind of implement these DSLs, plus leveraging what exists already today, for example, to take input from machine learning algorithms, from scientific algorithms developed in mathematical packets, right? Or actual already MLIR representation. We have been general here, but like this is all a set of front ends that you can plug into the MLIR system. Then, like, you can lower into a common representation, but each of the common representation that can be specialized to solve specific compilation problems with the so-called MLIR dialects, right? And like next slide, you see one of the dialects that we are most proud for. is our SODA dialect that enables us to generate accelerator to level synthesis, just push button using TensorFlow. But basically, like, we'll extend what we have today to also support this new analog accelerator that we are thinking to integrate, and like enabling the support for heterogeneous components from the codes. Right. One of the great things that you can do is that if you have components off the shelf with a backend in LLVM, they can be already plugged in, provided there's still work needed, right? But it's conceptually much easier than before. So. To move a little bit more, our example. So this is basically what we can do already today with SODA, the software-defined architecture toolchain, which is our framework to generate custom accelerators starting from high-level, very high-level specification Python. Our example here is Llama, right? And then through the compiler techniques, partition your specification and synthesize. Literally synthesized through an high-level synthesis tool that will take your optimized IR into Verilog design, and then connecting it to the open road toolchain from Andrew Kang from UCSD to fully open source, generate the RTL, the GDS2, so the mask ready for prototyping of the tools. Now, this is the two examples here. Is you take Llama, identify the key block, obviously the transformer function, right? It's literally one command, you partition it out, set optimization parameters that you want. You can also do automated design space exploration, and then that's what you generate, right? An architecture, for example, targeting 200 megahertz, or an architecture targeting 500 megahertz. You see, visually, you already see the difference, right? The 500 megahertz is the same area. It's basically all full because we started adding a lot of components to increase the performance. In 200 megahertz, we have much less significant constraints for the performance, right? So we use less area. This is done with the 45 nanometer technology, which is just predictive, but with SODA, we also have a prototype going on. Fully is in packaging right now, using Skywater 130 nanometer. Sorry. Yeah. That would be.
Pause for water.
Yeah.
Yep.
Sorry about that. I get excited talking about soda and water. But then Nicholas tells me that we are going to have soda and whiskey, so. Okay, sorry about that. Last, prototyping and chiplet integration, right? We have in our team people that are big expertise in doing prototyping, like Columbia is the ESP platform. Didn't say in the previous slide, but one of the targets that we already use to test our stuff, obviously Soda, leverages Panda Bamboo, which is a tool that I started in Politecnico di Milano when I was a PhD student. So it's basically has 20 years now of history. And I was born targeting FPGAs. So we can directly integrate stuff that goes on FPGA. ESP is this nice tiled-based platform that can prototype for you what, with the latency-sensitive theory, what you think could be a potential chiplet-based system with an active interposer. It's great, and we are keep using it to connect our custom accelerator site into the system on a chip. In that case, that will become a system in a package next, right? And like this is. One of the big resources to do internal prototyping and validation before going to tape out. But then, like with UCSD and zero ASIC capabilities that are like zero ASIC has a very interesting process today. Just before any fabrication, they validate everything with open source tools. And Andreas also funded a lot of the development of OpenRoad and also a lot of the development of Soda when he was DARPA program manager. So like we know very well each other, right? We know how to integrate. And like the next step to this is obviously moving to the external prototyping capabilities, as Jim was saying. So interfacing with the resources from Natcast and APMP, showing that like open source is a viable opportunity to get to results that are ready to be prototyped. Then, sure, we may want to use commercial tools, right? We will have already the validated chips, and then the commercial tools can take over for the last step, but we won't need that to kind of do all our design and develop all our concept up to, and actually down to, like, what would be a chip characterization, right? And that's the great part and the great, I think, democratization that we get here, because everybody can access open source tool, right? And do this design. And in fact, like, once you have all this trust put together, we have really a set of capabilities to do design space exploration, like deciding, giving a problem, deciding our chiplet system is going to be designed, using the open source co-design tools to find the right balance, simulate, and then generate the chiplet design. And then like going to this concept system testbed that will enable us to measure the results in a much more relevant way, right? Because like we get the actual prototype that can also feed back the information. The other great thing, we talked a lot about AI. This is all open source. So if you want to construct copilots or AI-driven hardware design tools, which we already have a big plan in Soda to do that, all the intermediate stages that you need, all the data are going to be available. It is not going to be possible if you take Synopsys or Cadence, right? Nothing against them, like it's created by Vincentelli, but you have a big, Vincentelli, by the way, was the supporter of this project. So, but you have a big opportunity here, right? That this will build that knowledge base on which you can train your models to do the optimizations and being then repeatable. And like inside like the commercial tools, the only thing you can declare is really for the licensing is the total area, not even showing the die, and possibly the target frequency, which is limiting for a paper, right? You cannot reproduce the results. So I think that's all for the technical trust, and I would like to Jim conclude.
Okay. Thank you, Antonino. Let's see, just a few closing comments, but one of the things you did indicate some of our gaps. So we're certainly investing in our project on the system software capabilities that support heterogeneous computing, the development of interface generators. One of the things that's difficult for us to do as a single project is to develop the standards for the physical, thermal, electrical protocols, et cetera, that are used for chiplets. So that's definitely something that we would be pointing to and counting on the CHIPS and Science Act R&D program, especially their investments in the National Advanced Packaging and Manufacturing Program. Now that program has been stood up. I learned this morning that there's some, there have been some staffing cutbacks within the CHIPS R&D program, as well as the CHIPS Manufacturing Incentive Program. So we're kind of holding our breath to see, if there are any disruptions to the previously announced research centers and capabilities that the CHIPS Act should be putting in place. But they haven't zeroed those activities, unlike some of the other activities. So we're optimistic that overall the CHIPS R&D program, the CHIPS Act, has bipartisan support within the U.S. and that their investments will largely remain intact. There might be some adjustments that are made by the new administration. But let me just sum up by saying that we're really focused on trying to democratize access to cutting-edge prototyping capabilities, and those capabilities are the ones that the CHIPS Act will be standing up. So we're not doing we're not prototyping within P&L and within our team. We're trying to apply co-design principles to develop designs that are suitable for prototyping. And those designs will be supported with software. Because the infrastructure that the CHIPS Act is establishing through the Department of Commerce, they give us a wonderful ability to tape out hardware prototypes and package them as chiplets or through 3D hybrid bonding or some other advanced packaging technology. But the NIST and the CHIPS program within Department of Commerce is not developing software. They're not developing algorithms. They're not developing a software stack or a compiler tool chain. So those are roles that we think DOE can bring to the table so that as soon as test chips are available, hardware prototypes are available, they can then be tested and evaluated with real workloads so that we can do more than just measure bandwidths and measure physical dimensions. So that's a key part of what we think we can contribute. The other factor here would be that this is what we see as a way to address the DOE's energy efficient computing and maybe the community's energy efficient computing objectives, and do so in a way that would leverage analog and digital accelerators in a co-design flow. Now, we're looking at 2 use cases for analog computing, but I'll mention that Antonino is a PI for another analog computing concept using chemical reaction networks. We have a mutual friend, Nicholas and Andrew Sloss, who's working at a startup company looking at reversible computing. That is another analog computing accelerator, in fact. And so those are things that we would also want to be able to work with, any advanced concepts for analog computing. And why do we think we can democratize co-design? It's because there's open source tools that we can use. You're not bound to the commercial tools. And Second, because we can talk about chiplets. So your design on innovation can be focused on that specialized accelerator that you want to develop. And you can largely reuse commercial commodity computing components for other processors, memory interfaces, network interfaces, et cetera. So that's kind of the bottom line for what we think DeCoDe can provide. And I'll just wrap up with a repeat of a slide that I shared last year. Some of the public open software repositories. These are both ours and our partners. So with that, we're happy to take questions.